A planet built for ambiguity shouldn't produce shapes this tidy. Yet in Gale crater images circulating as Curiosity rover photography show polygonal fracture networks that lock together like a honeycomb. The geometry is seductive. Our brains want one clean conclusion: water, ice, or a climate story you can summarize in a sentence. But polygons can't prove global climate change. What they can do is constrain local volatile history, how water, ice, or brines may have interacted with rock at specific times and places. So treat this like a crime scene. No leaps, no smoking gun, just competing hypotheses and the measurements that could eliminate them. One precision note up front: a specific proper name has been circulating online for this outcrop, but unless we can confirm it in official NASA or JPL captions rover planning products or PDS metadata, we won't use it. And unless we can confirm the exact image IDs and ASOL numbers, we'll describe this as imagery circulating as curiosity material rather than asserting a specific target. Polygonal terrains themselves are common on Mars. Orbiters have seen them across latitudes and elevations, etched into plains and crater floors. Curiosity's advantage is intimacy. It can approach a target, document textures up close, and test chemistry. And sometimes it can add stereo context or drill for mineralogy. But those capabilities vary by target, safety, time, and campaign approval. CheMin mineralogy in particular requires a drilled sample. The core question isn't whether Mars can make polygons. It can. The question is which process made these polygons here and when. On Earth, three major pathways often compete to explain polygonal cracking. One, desiccation: mud dries, it shrinks, stress builds, cracks open into polygon networks. If that surface is buried and later lithified, the geometry can be preserved for geological time. Those cracks may later become veins if minerals precipitate inside them. Two, thermal contraction in ice-rich ground. In permafrost, ice-cemented material contracts as temperatures drop and can crack repeatedly, often on seasonal cycles. Over time, those cracks can reopen and be filled by sand or ice. Even if the ice later disappears, the structural pattern can remain. 3. Mineralized fracture networks. Rock can fracture for many reasons: burial stress, unloading as overburden erodes, or impact-related stresses. Later, fluids can migrate through fractures and precipitate minerals. That can create polygonal networks that look like mud cracks, even though they formed long after deposition. In that case, the polygons record a subsurface plumbing system, not a drying surface. On Mars, all three are plausible in different settings. And frustratingly, polygon shape alone, how hexagonal it looks, doesn't uniquely diagnose the cause. So what would actually discriminate the scenarios? Start with where the cracks live. If a polygon network is confined to a single bedding surface, one layer acting like an exposed skin, desiccation becomes more plausible. If fractures cross-cut multiple beds or ignore bedding boundaries, that pushes probability toward later fracturing and mineralization. Then look at margins and fills. Desiccation cracks can taper downward and may preserve soft sediment textures if exposed. Ice-related polygons can show evidence of repeated opening and wedge-like fills. Mineral veins tend to have sharper cemented boundaries, sometimes with subtle halos of altered chemistry around the fracture. Curiosity can't trench freely to reveal perfect cross-sections, but it can still build a case. Mastcam provides context: how the polygons sit relative to layers, slopes, and neighboring units. Molly can examine crack margins and grain-scale textures. ChemCam and APXS can test whether bright fracture fill differs chemically from the host rock. And only if a drill campaign is approved and the target is safe and suitable, CheMin can identify minerals directly from a drilled sample. That's the difference between pattern recognition and inference. Here's a concrete way to think about it. If close-up imaging shows fractures that terminate at a bed boundary and the chemistry of the fill matches the host, the balance shifts toward a mechanical cracking event tied to that specific layer. But if the fill chemistry is distinct, say enriched in salts relative to the host, and you see consistent vein-like cement, the balance shifts toward mineral precipitation from fluids moving through fractures after the rock formed. Notice what's missing from both cases: certainty from geometry alone. Without site-specific mineralogy, without topography where available, and without a mapped stratigraphic context, tying the polygons to a particular unit and cross-cutting history, the honeycomb remains a clue, not a conclusion. Even so, the polygons still tell us something real. They record stress strong enough to fracture coherent material in organized networks. And in many geological settings, organized polygonal cracking is associated with volatiles: water in mud that later dries, ice-rich ground that contracts, or fluids that circulate and leave minerals behind. The disciplined takeaway isn't "this proves an ancient lake" or "this proves permafrost." It's that Gale Crater's rocks preserve episodes of cracking, and that episodic involvement of volatiles is plausible. While the timing could range from near-surface conditions during deposition to later burial and diagenesis to much later climate episodes. That's also why you have to be careful with planet-wide claims. A single fracture field can't safely carry a global climate narrative. Polygons can be intensely local, controlled by rock type, cementation, grain size, slope orientation, thermal properties, and pre-existing weaknesses. So what would move this forward in a way that survives skepticism? 1. Anchor the outcrop to confirm mission records, image IDs, sol numbers, and official captions. 2. Quantify morphology, polygon diameters, junction angles, crack widths, and whether the features are ridges or troughs. 3. Test composition, especially any bright fill or cement. 4. Read timing from relationships. Do fractures stop at boundaries, cut across layers, or get overprinted by later features? That's how planetary science stays honest. Curiosity's honeycomb isn't proof. It's a discipline question. Was this a drying surface, frozen ground that cracked again and